Another test for convergence or divergence of a series is the comparison test. Now here in this test we compare a given series with a series which is already known to be convergent or divergent. For example, we may compare the given series with the harmonic series or the P series in general, or geometric series. I mean one of the series that we can determine easily whether they are convergent or divergent. So the test says that if you have two series, A and series A sub n and the series B sub n, but provided that those two series have positive terms. So the series, we are given this series to be tested, and we find the series B sub n and then we compare the two series, and these series have the terms of these series should be positive terms. Now we have two cases. If Bn, if the series that we find is greater than the series A sub n, the series that we want to test, then that means if this is convergent, then the series that we want to study is convergent. If we can find smaller series B sub n, and we want to test if our series A sub n is convergent or divergent, and we find that the smaller one is divergent, then as a result the larger one will be divergent. So if we can find a bigger series or larger series and that series is convergent, then our series is convergent. If we can find a smaller series, smaller series, and that series was divergent, then the larger series, our series will be divergent. And I used here Venn diagrams just to explain the idea, but actually we don't represent them using the series using Venn diagrams. I mean circles or something similar to circles. But we usually represent them as dots. Okay, let's erase this part and apply this here. Okay, so for part 1, we know that the larger series that we already found is convergent. That means the smaller that we want to test is convergent. If the series that we found is smaller than the series that we want to test, and that series is divergent, then our series will be divergent. Now let's take an example. We have the series 3 to the nth over 5 to the nth plus 1. Now A sub n is 3 to the nth over 5n plus 1. Now this is the series that we want to test. This is the general term. Now we try to find another series from this series, or a series that can be compared to this series. And that it's a good idea to start from what we have. We have this series, and we notice that by looking at the series that the plus 1 here in the denominator is the only thing preventing the series from being geometric. So this is less than 3 to the nth over 5 to the nth, and this is, as you know, this is geometric, a general term of geometric series, because this can be written as 3/5 to power n. This is r to the nth. So we can compare our series with a geometric series. Now the geometric series that we have is convergence series. Why? Because if you look at r, the absolute value of r is 3/5, and that is less than 1. That means this is convergent series. If the larger one is convergent, then our series 3 to the nth over 5 to the nth plus 1 is convergent. Let's take another example. We can write here by the comparison test. Part 1. Another example, we have the series 5 over 2n squared plus 4n plus 3. Now if we look at this series, the a sub n is 5 over 2n squared plus 4n plus 3. This is a sub n. Now we need to compare it to other series. So this is less than 5 over, let's take the first term of this. And this is 5 over 2, 1 over n squared. But this is a known series. This is one of the p series, because if you remember from previous video, this is called p series. And we have two cases. If p is greater than 1, then it's convergent. If p is less than or equal to 1, then it's divergent. Now we take the sum 5 over 2, 1 over n squared, and from 1 to infinity, and since this is constant, we can pull it out of the sum, and 1 to infinity, 1 over n squared. Now this is p series with p equals 2, and that's greater than 1. That means it's convergent. This series is convergent, and using the comparison test, the series from n from 1 to infinity, 5 over 2n squared plus 4n plus 3 is convergent as well. Let's take another example. The series natural log n over n, is it convergent or divergent? Now a sub n is natural log n over n, and this is less than 1 over n. 1 over n is well-known series. 1 over n is p series, well-known series. It's harmonic series. It's called harmonic series. So 1 over n, for n greater than or equal to 3, we can try some values. For example, for when n equals 2, we have natural log 2 over 2, but natural log 2 over 2 using calculator, we get a number 0.35. It's approximately 0.35. And the right hand side is 1/2, which is 0.5. So this is less than 1 over n. So what about n equals 3? Now for this natural log 3 over 3, using the calculator, we find this it can be approximated as 37.37, and natural log 1 over n is 1/3, and 1/3 is 0.33, etc. This is greater than. So, and we can test all some terms greater than or equal to 3. We find that the left hand side, our series, is greater than ln over n. Natural log of n over n is greater than 1 over n for all n greater than or equal to 3. Okay, so that's what we need actually. So a sub n, natural log n over n, is greater than 1 over n. Now we take the series of this, series of 1 over n. This is harmonic series, which is part of p series. P is equal to 1, p equals 1, it's less than or equal to 1, and that means it's divergent. So the smaller series is divergent by using the comparison test. Part 2, we find that if the smaller is divergent, then the larger is divergent. Our series natural log n over n from 1 to infinity is divergent. Now sometimes our test, this comparison test, doesn't work, but we can work on that test using limit. So sometimes we have what we described so far is that if we have a series a sub n and we could find a smaller series that is divergent, then our series is divergent. But what if we find a series that's, if the smaller one is convergent? What if this is, if our series, we want to test a sub n and we find that the smaller series is convergent? Can we say something about a n? No, because here we can find some series that's divergent. So if the smaller is convergent, our test is inconclusive. But what should we do in this case, or what can we do in this case? We have another test that's called limit comparison test. It modifies the comparison test. It's called limit comparison test. The limit comparison test, for example, if we have series a sub n where bn is less than or equal to an, we could find smaller series, but this is convergent. What can we say about a sub n, the series a sub n? In this case, we can't tell anything about this series, so we need the limit comparison test. So limit comparison test says, suppose that the series a sub n and the series b sub n are series with same condition, with positive terms. Now if the limit of the ratio a sub n over b sub n is equal to some constant, positive constant, some positive constant that's for sure less than infinity, some constant, positive constant less than infinity, any number greater than 0, and then we can test, then the series, then both series are convergent, or both series are divergent. What does that mean? That means if we know bn, that bn, the series that we generated, is convergent, then our series is convergent. If it's divergent, then our series is divergent. So the conditions are the series have positive terms and this ratio is true. So this is the test. Let's apply it here. For example, we want to check if this is convergent or divergent, and from 1 to infinity, is it convergent or divergent? So the series a sub n, this is a sub n. A sub n is 1 over 2n minus 1. If we generate bn from this, I mean bn, just we want to find a known series from this series. As you can see, the problem here, the -1 is the only thing preventing the series from being geometric. So we can define bn to be 1 over 2 to the nth. This is geometric because this can be written as 1/2 raised to power n, and that's convergent. Okay, now we could find two series that have positive terms, and now we need to find the limit of an over bn as n goes to infinity is limit of 1 over 2n minus 1 over 1 over 2n, n goes to infinity. Flip the denominator, you get 2n over 2 to the nth minus 1, n goes to infinity. Now divide each term by 2 to the nth, you get 2 to the nth over 2 to the nth, divide each term by 2 to the nth, and n goes to infinity. Now this gives limit of 1 over 1 minus 1 over 2 to the nth. Now we substitute n goes to infinity and infinity, so this becomes 0, we get 1. So 1 is less than infinity, it's positive and less than infinity. That means we can apply the limit comparison test. But now by the limit comparison test, we know that, and knowing that the series 1 over 2 to the nth n from 1 to infinity is convergent, the other series, or the series under study, our series is convergent. If one of them is convergent, the other one will be convergent. So this is convergent. Now let's take another example. If we have the series 2n squared plus 3n over square root 5 plus n to the fifth, and from 1 to infinity, is this convergent or divergent? Now we determine a sub n. This is a sub n. So a sub n is 2n squared plus 3n over square root 5 plus n squared, and as you can see, it has positive terms. You can substitute n equals 1, 2, 3, 4, etc., and you get positive values or positive terms. Now we need to find bn. We find bn from this series by just considering the term with the highest power of n. For example, we can take this from the numerator, 2n squared, and we can take this from the denominator, which is, now this is 5. So 2 to 5 over 2, because this is under square root, so it becomes 5 over 2, the power. Okay, so this is our new series. We can simplify it to get 2 over n to 1/2. Okay, now this is a series with positive terms. Now we apply the limit as n goes to infinity of an over bn. This is limit of 2n squared plus 3n over square root 5 plus n to the fifth over 2 over n to the power 1/2. N goes to infinity, and then we simplify this limit. We find that now we flip this, multiply it by the numerator, we get 2n to 5/2 plus 3n to 3/2 over 2 square root 5 plus n to the fifth, by multiplying by the reciprocal of the denominator. Now limit n goes to infinity, we divide each term by n to 5/2, and we get 2 plus 3 over n over 2 square root 5 over n fifth plus 1. And then after that we substitute the limit. We find that this becomes 0, this becomes 0. We get 2 over 2, which is equal to 1, less than infinity. And that means Bn, the series Bn, which is 2 over n to 1/2, and we can pull this out of the sum, 1 over n to 1/2. The power here is 1/2, less than 1. That means this is divergent. This is P series. So P is divergent. By the limit comparison test, our series A sub n, which is 2n to 5 halves plus 3n to 3 fifths over 2 square root 5 plus n to the fifth, is convergent. It is divergent. Now the last thing in this video is this is section 11.5. This will talk about alternating series. Alternating series is a series whose terms are alternating positive or alternating terms. That means alternately alternately positive and negative. For example, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, and on it goes. Now this can be written as sum from 1 to infinity, 1 over n, but this is the sign, sometimes positive, sometimes negative. So this is -1 to n minus 1. For example, when n equals 1, we get -1 to 0 is 1, we got positive value. When n equals 2, we get 2n, 2 minus 1, 1, the power of -1 is 1. That means we still have the negative sign. So this is of the form, the general form, -1 to the power n minus 1 bn. Bn in this case is 1 over n. Another example, -1/2 plus 2/3 minus 3/4 plus 4/5 minus 5/6 plus 6/7, and on it goes. This is sum from n1 to infinity, -1 to the power n, because the negative appears in the first from the beginning. So when n equals 1, we have negative sign, times n over n plus 1, and the general form of this series is -1 to the nth times bn, where in all these cases, now this is bn is positive. Now the test here says if the alternating series sum n1 to infinity, -1 to n minus 1 bn, which is b1 minus b2 plus b3 minus b4, etc., where bn is greater than 0. If this satisfies the two conditions, first, bn plus 1 is less than or equal to bn. That means it's decreasing. The terms are decreasing for all for all n. And the second condition is that limit of Bn as n goes to infinity is equal to 0. If those conditions are satisfied, then the series is convergent. Let's take an example. For example, 1 minus 1/2 plus 1/3 minus 1/4, the one that we talked about it here, which is an example of alternating series. This is sum of -1 to n minus 1 times 1 over n from 1 to infinity. This is Bn. This is the series Bn. So we want to check the two conditions. The first condition is Bn plus 1 is less than or equal to Bn. That means the next term is less than the previous one, the current one. That means the sequence is decreasing. So let's substitute n plus 1 into Bn. So Bn plus 1 becomes 1 over n plus 1. Bn is 1 over n. Just substitute n plus 1. Now this is Bn plus 1. What about Bn? It's 1 over n. As we can see, this is less than 1 over n plus 1 is less than 1n for all n greater than or equal to 1, or for all n, because we know that n means 1, 2, 3, natural numbers. So the first condition is satisfied. Now the second condition is that the limit of Bn as n goes to infinity should be 0. Now limit of 1 over n goes to infinity is 0. 1 over infinity is 0. So the two conditions are satisfied. So the series is convergent by the alternating series test. Another example, the series -1 to n times 3n over 4n minus 1, n from 1 to infinity. Now this is Bn. The first condition, Bn plus 1 less than Bn. So substitute n plus 1, you get 3 times n plus 1 over 4 times n plus 1 minus 1. And this is 3n plus 3 over 4n plus 3. And Bn is 3n over 4n minus 1. We can compare them by testing some values, and we find that this is true for all n. Or if it's not easy to do so, we can find the derivative. We can take Bn, consider it as a function of x, 3x over 4x minus 1, and then find the derivative. Denominator minus the derivative of the numerator times the numerator minus the numerator times derivative of the denominator over denominator squared. So we have 12x minus 3 minus 12x over 4x minus 1 squared, and we cancel these. We get -3 over 4x minus 1 squared, and since the denominator is positive because it's squared, the numerator is negative. That means this is less than 0 for all n. So we have two methods to show that the sequence or the series is convergent, is decreasing. The terms are decreasing, either by just plugging n plus 1 and plugging n and compare them. If we find Bn plus 1 is less than Bn, from that's it. Or we can find the derivative of Bn by converting it into, change the variable into x, and finding the derivative. If the derivative is always less than 0, that means it's decreasing. Now the first condition is satisfied. The second condition, limit bn as n goes to infinity, is limit 3n over 4n minus 1, n goes to infinity. So we divide by n. Dividing by n, we get 3 over 4 minus 1 over n, n goes to infinity. This is 0, we get 3/4. This is not equal to 0, so it's divergent. It's not convergent. Not convergent. Another example. The series -1 to n plus 1 times n squared over n cubed plus 1 n from 1 to infinity. Is this convergent? We have bn, the general term bn is n squared over n cubed plus 1. So the first condition is that it's decreasing. We want to show that this is decreasing. Pn plus 1 is less than Pn, but it's not easy to do so by just plugging n plus 1 and Pn. So we convert this into a function of x. It's x squared over x cubed plus 1, and find the derivative. The derivative is the denominator plus derivative of the numerator minus numerator times derivative of the denominator all over denominator squared. Now simplifying, we get 2x minus x to the 4th over x cubed plus 1 squared, and this is x times 2 minus x cubed over x cubed plus 1 squared. We find that we only consider x is greater than 0, because this is equivalent to n, but so n is positive, x is positive. Now f prime of x is less than 0 only if the numerator is less than 0. So x times 2 minus x cubed is less than 0. Since x is greater than 0, we can divide both sides by x, and we get 2 minus x cubed is less than 0 because we divided by 0 by x. 0 over x is 0 since x is not equal to 0. Now we solve this. 2 is less than x cubed, then take cube root of both sides. You get x is greater than cube root of 2. So on the interval cube root 2 to infinity, the f of x is decreasing. So that means fn plus 1, I mean bn plus 1, is less than bn for n greater than or equal to 2. Now the second condition, this is the first condition. The second condition, limit bn, n goes to infinity, is limit n squared over n cubed plus 1, n goes to infinity. Now we divide by n cubed, limit n squared over n cubed over n cubed plus 1 over n cubed, n goes to infinity. This is 0, equal to 0, and that means it's convergent by alternating tests, by the alternating test.